I'm your host, Dr. D. Welcome to Math in the House. Today, we're doing Math Analysis, Chapter 7, Section 3, Vectors. I'm your host, Dr. D. Okay, so this next section is on vectors. Now, a vector is simply a magnitude and a direction. So, examples of these: displacement, that could be a vector. 5 miles due south. 5 miles is the magnitude. How far is it? Which direction? Due south. Another example: velocity. What's the magnitude? 50 miles per hour. That's a velocity at 30 degrees from horizontal. So basically, if I'm shooting a missile at 30 degrees from horizontal, that's the direction, and it's going 50 miles per hour. So magnitude, direction. Now, acceleration is 32 feet per second squared. Now, what direction? Straight down. So once again, we have a vector quantity. We could have force, 200 pounds, parallel to the water. So that would be an example of a force in a particular direction. So vectors are magnitude plus direction. Now, scalar is a magnitude only. So if we take the scalar quantity of displacement, that would just be distance, and that's just plain 5 miles. The scalar quantity of velocity would be speed. That's just 50 miles an hour. Now, if I say 50 miles per hour at a particular direction, that's a vector. If I say just plain 50 miles an hour, that's just an amount, a magnitude. Same thing with acceleration. 32 feet per second squared is an acceleration, but it's only a vector quantity if I give you a direction. With no direction, it's scalar. And then a mass of 200 kilograms. There's no direction with that. It's just the amount of material. Whereas a force has a direction.
Bam! Do we have that in a Christian school?
That's annoying. Hold on. Now, let's check out the graph. Okay, we have 3 vectors here. Vector AB, vector CD, and vector EF. Now, all 3 vectors are equal. Why? Because a vector equals its change in x, comma, change in y. Notice AB goes 4 right and 2 up. So its vector is 4, 2. Now, CD goes 4 right and 2 up. EF goes 4 right and 2 up. So all 3 of these vectors are 4, 2. Now notice the symbol for an ordered pair or a location is parentheses. Like 0, 0. That's parentheses, that's a location. But a vector, you use these pointy looking things that says you go 4 right and 2 up. Now, if I was going left, then the x would be negative. If I was going down, the y would be negative. And notice one other thing. AB, the vector AB, the symbol for vector is the same as if it was line segment AB, only you put a half an arrowhead up on top. Not a full arrowhead, just the top part of the arrowhead. So that says it's a vector. Okay, so let's cruise onward. So here we have vector A. And notice vector A goes 8 right and 5 down. So that means the vector A is 8, -5. So the first number is the horizontal component, the second number is the vertical component. Now, theta is the direction of vector A. Remember, that's important. You need a magnitude and a direction. So theta being the direction of angle A, how do we get theta? Well, theta is going to be inverse tangent of the y over the x. Inverse tangent of the change in y over the change in x. So in this case, it's inverse tangent of -5 over 8, which turns out to be negative 32.01 degrees. Now, we would rather always have positive thetas. So really, our theta here is going to be the angle all the way around like this, which would be 327.99 degrees. So that's theta, 327.99 degrees. That's my angle, or that's my, direction of vector A. Okay, now, if I want the magnitude of vector A, which basically means the length of it, I show that by putting these absolute value signs over it, which is really a notation. It doesn't mean absolute value. It simply means get the magnitude of vector A. Well, that's just going to be the change in x squared, change in y squared, add them up, take square root of the whole thing. That's basically the distance formula. So we go 8 squared is the x direction, -5, square that, that's the y direction. Remember, -5 squared, it's not 5 squared then make it negative. It's the whole -5 squared, so it makes it a positive 25. 64 and 25, 89. So the magnitude of vector A is the square root of 89. The direction is 327.99 degrees. Okay. Oh, and in this section, the angles will all be degrees. So that means when you're using your calculator, remember that. Okay, now, vector V is 8, -15, and it begins at 5, 3. Now, notice back at the beginning, I forgot to mention something. Oh, it's the, okay, let's go back to here. Back here, AB is called a position vector because it starts at the origin. Even though AB, CD, and EF are all equivalent vectors, you can move a vector anywhere you want. If you started at the origin, it's called a position vector. Okay, back to the ranch.
Bam! Do we have that in a Christian school? That's annoying.
Hold on. Okay, so we have vector V is 8, -15, which means it goes right 8, down 15, and it begins at 5, 3. We want the coordinates of the endpoint. So we're going to go to our graph. Now, what I'm going to have to do is make every block 2. So 5, 3 is going to be 2, 4, 5, 3. There's 5, 3. And now the vector is 8, 15. So I need to go 8 to the right. So 2, 4, 6, 8. And then down 15. So 2, 4, 6, 8, 10, 12, 14, 15. So there is vector V. Now, where is its endpoint? Well, I could look at it on the graph and say its endpoint is at 10, 12, 13, down 2, 4, 6, 8, 10, 12. So 13, -12. And Remember, we started at 5, 3. Now, I did that by the graph. Now, you can also do it by algebra. So, if I start at 5, 3, then the end point is going to be 8 to the right of 5. So, 8 plus 5 is 13. And it's going to go down 15 from 3. So 3 minus 15 is negative 12. So 13, negative 12 is the endpoint. So like I said, you can do it with the numbers or you can do it with the graph. Now, find the magnitude of A. Well, the magnitude of A is simply, well, let's go back to the graph and you can see, okay, what I have is a triangle here. The magnitude of vector V is this. And so I know I'm going right 8 and down, let's see, yeah, right 8 down 15. Yeah, because 3 minus 15 is negative 12. So there's my 8, 15, and I just need the hypotenuse. Well, I happen to know 8, 15, 17 is a Pythagorean triple, so the magnitude of angle V is 17. But let's say we're not privy to that information. Well, we need to do by algebra. So the magnitude of vector A is going to be the square root of x squared plus y squared. So 8 squared plus negative 15 squared. So that's going to equal the square root of 64 plus 225, which equals the square root of 289, which equals 17. Bam! Now, notice the magnitude is always positive because the magnitude, it's an absolute value. It's always going to be positive. Now, the direction of A. Well, going back here, what we want is just the theta right here. So, tangent theta equals negative 15 over 8, opposite over hypotenuse. So that means theta is going to be the inverse tangent of negative 15 over 8. And when we do that on our calculator, we end up with 15, change signs, enter 8 divided by inverse tangent in degrees, negative 61.93 degrees. So we'll just say negative 61.9 degrees. Now that makes sense. That looks like it could be a 61.9 degree angle. But remember, we don't want that angle. We want the angle all the way around here. So what I do is I add 360 to that, and I end up with 298.1 degrees. So direction of angle A, theta, or direction of vector A, theta equals 298.1 degrees. Remember, vectors are magnitude and direction. So we could describe vector V. Oh, I keep calling this vector A. Yeah, that's vector. We called it vector V up there. So watch the magic. I'm just going to okay, all this time we thought we were talking about vector v, we're actually talking about vector A. Okay, see, there's more than one use for that sound effect. Okay, so vector A is 8 right, 15 down, or we could say it's 17 in the direction 298.1 degrees. And once again, we just change to vector A. Okay, cruising onward. Now find the horizontal and vertical components of a vector. So this time we're going to be given, instead of, in this example, we're given the horizontal and vertical components, and we found the magnitude and the angle. Well, here we're going the other direction. If we're given the magnitude and the angle, then we want the horizontal and vertical components. So notice, here's vector A. It goes left some x value and up some y value. Now we're going to say theta is the whole angle all the way to vector A. So that's really the angle we're looking for. Theta sub r is the reference angle for vector A. So notice cosine of theta sub r is x over the magnitude of vector A. So notice adjacent over hypotenuse is cosine. And then sine of theta sub r is opposite over hypotenuse, the y value divided by the magnitude. So what that gives us is then x equals magnitude times cosine of the angle, and y equals magnitude times sine of the angle. Let's try an example. We're given that vector A is 5 meters per second, so this vector is in France, of course, and the angle is 130 degrees. So that's basically what we're shown right there. Find the magnitude of the x direction and the magnitude of the y direction. So what we do is we just say x, well, let's be more proper with the notation here. So the magnitude in the x direction is going to be the entire magnitude of the vector, which is 5, times cosine of the angle. Now we're just going to use 130, because notice when we go cosine of 130, that's going to show that the magnitude in the x direction is negative. And the magnitude of the vector in the y direction is 5 sine of 130. So we just crank that out in our calculator. And so cosine of 130 is negative 0.64278. And then we multiply that by 5, and we end up with negative 3.21. And I'll just make it negative 3.2. And then 5 sine of 130 is 3.83. Oh, and this is meters per second, because the vector is a velocity vector. Okay, so notice we could have used, if the angle is 130, we could have used 50 degrees here. But if we had used 50 degrees, we would have had to reason to ourselves, we would have just end up with 3.2, and we'd have had to say, well, x is negative because it's going left, and y is positive because it's going up. But if you just use the 130 degrees, your sine and cosine will take care of the sines. So basically what we've done is found the horizontal and vertical components of vector A. So 3.2 meters per second left and 3.8 meters per second up gives you a total vector of 5 meters per second at 130 degrees. Okay, cruising onward. Vector addition. Now, if we're adding two vectors, then the direction is going to keep it from being as easy as just adding the magnitudes. Now, if the vectors are going the same direction, then I just add the magnitudes and I'm done. Like if I have a tug of war and everybody's on one side, I just add up all the forces. Now, if I have everybody on the other on opposite sides, then I'm subtracting forces. But in this case, we have one force A going up and to the right, and force B going down and to the left. What's the resultant force? What's the sum of those two forces? It's going to be this red force. Now, here's how this works. Vector A is 4, 2. So I go 4 right, 2 up. Vector B is -1, -3. So I go 1 left, 3 down. Now, if I want to add vectors A and B, then all I do is add the two x's, add the two y's. So the x's are 4 plus -1 is 3. And the y's are 2 plus -3 is -1. So the resultant vector in red is right 3, down 1. That's where these two vectors would end up. Now, there's a geometric way of showing that. And what we do is we make a parallelogram. So you've got the blue vectors. Well, I make my parallelogram from the head of A, I make it parallel to B. And then from the head of B, I make parallel to A. And then what you end up with is the diagonal of the parallelogram is the sum of the two vectors. Now, I could do the same thing with what we call a triangle method. Remember, I don't have to have the vectors starting at the origin like they're doing here. I could have vector A start at the origin and then vector B start from the head of A. So notice vector A and B both start here. Well, I just go vector A. Now I'm going to take vector B and put it right here. So it's here. Now the sum of the vectors is just where my second vector ends up. So you can do the parallelogram method or the triangle method to show it geometrically. But algebraically, it's really simple. Just add your x's, add your y's, and bam, you have the sum of the vectors.
Bam! Do we have that in a Christian school? That's a no. Hold on.
Multiplication of a vector with a scalar. Remember, a scalar is just a plain number. So here's a quick example. 3 miles per hour times 2. That's just 6 miles per hour. So that's all you're doing. Take any vector, multiply it by the scalar, and you have just a different vector. Now, unit vectors. Vector I is 1 unit to the right and none up and down. Vector J is 1 unit up and none to the right or left. So basically, vector I is 1 unit in the x direction. Vector J is 1 unit in the y direction. So if I want to show a vector 3, -4, I can express that in terms of unit vectors. How? Well, 3 is saying I'm going 3 units to the right, and -4 is saying I'm going 4 units down. So 3i minus 4j is just another way of saying the vector 3, -4. Piece of cake. Okay. Now, the resultant vector. How do we find the resultant vector? We find the x and y components of each vector. We add all the x's together, and then we add all the y's together. Then we use the Pythagorean theorem to find the magnitude of the result. And if we want to know the angle, we use the tangent function to find that direction. So it's going to be tangent of y over x. Tangent theta equals y over x. So that means theta is the inverse tangent of y over x. Okay, so let's check that out. Two offensive linemen. This is football, in case you didn't know. So we have two offensive linemen that are double teaming a defensive tackle. So we've got these two offensive guys, and they're pushing this defensive guy. So vector A is the force from the right offensive lineman. So let's say he's the right guard, and B is from the center. So these two guys are pushing this one defensive tackle, and they're trying to push him backward. But one pushes at that angle, the other pushes at this angle. Now what we want to know is how much total force is being exerted on the defensive lineman. So what's the total force that these two vectors are giving? Now remember, we could do the parallelogram method. So I'm going to start from B and make a parallelogram parallel to A, a side parallel to A, and then I make a side parallel to B. And so my net force is going to be, well, okay, we're going to see that in the next slide. But if I want to get the, okay, so the vector A is 180 pounds at 120 degrees. And then vector B is 150 pounds at 45 degrees. So we want the total force exerted on the defensive tackle. All right, so the x component of A is going to be 180 times cosine of the angle. The y component of A is going to be 180 times sine of the angle. Now, I look at vector B and do the same thing. Vector B, this a little bit weaker guy, he can only push 150 pounds times cosine of his angle. And then the y component is 150 sine of his angle. So now what I've gotten is the x component of A and the x component of B, the y component of A, the y component of B. So what I'm going to do is add the x's, add the y's. So the sum of all the forces in the x direction are -90 and 106.1. So it's going to be 16.1 pounds in the x direction. So that means they're trying to push the guy up, and they're pushing him a little bit to the right because the guy in the offensive lineman on the left is a little bit stronger. So now, the sum of the forces in the y direction are going to be 155.9 plus 106.1, which is add the y forces, and I get 262.0 pounds. So there's my x force, my y force. Now if I want the total force, then I need the hypotenuse between this x and this y. So I square the x, square the y, add them up, take square root of the whole thing, and I end up with 262.5 pounds. So this is why in football you see offensive linemen ganging up on one defender because two guys can push a lot harder than one guy. Now, here's the problem. These two guys are ganging up on that one guy, so there's some defensive player that's left all alone that has nobody pushing on him. He could be coming through in a hurry. Okay, now what direction are they pushing? Well, remember, the direction is the inverse tangent of y over x. So we take the sum of the y's, 262.0, sum of the x's, 16.1, divide it, take the inverse tangent, and you get 86.5 degrees. So my resultant force in purple here is the diagonal of the parallelogram. And that's going to be 262.5 pounds at just a little bit right of 90 degrees, 86.5 degrees. The resultant force is going to be 262.5 pounds at 86.5 degrees, just slightly to the right of 90 degrees. That's it. Game over. Have fun with these.